For UAV, it could be gyroscopes, accelerometers, magnetometers, and all that.
Exactly. So last lesson I talked about your IMU, right? Your inertial measurement unit. Uh, so this entire thing, it would not be possible at all without that one single sensor. In fact, I think I'm not sure the specifics of this, but maybe it just uses that sensor and maybe a camera sensor to detect how big that hole is. It needs no other sensors to work. As for these two examples, yeah, they're not traditional sensors, but you might have something like a force sensor to detect how hard the impact was on this ground surface. And as for this particular humanoid robot, it's again like you have contact sensors to detect whether or not the feet are touching the ground, whether the feet have impacted the ground at with a large force. Yeah. It also has LiDAR sensors. You can see the lights here. So they basically tell you how far objects are with respect to the robot. Okay, so obviously the things that you are going to do in this lesson will not be as complex as what you've just seen. I just wanted to give you guys an example as to what you will be doing. In fact, my master's thesis involved, designing some algorithm, testing, slightly designing and mostly testing out algorithms on some complex problems. So if you end up choosing like to do a master's in robotics, this is what you might end up doing. So let's talk about the simplest form of a controller. It's called an on-off controller or a bang-bang controller. So the example of a heater that I showed you a couple of slides back, right? So that is an example of an on-off controller. So what an on-off controller is you can sort of guess by the name. It is a controller that rapidly or abruptly switches between its two extreme states. So in the case of a heater, there's two states would be on or off. So there's no intermediate state. So these sorts of controllers are actually very good for these sorts of applications, and they're quite simple to implement as well. So if you turn on your heater at some point, and if say the temperature reaches its required value, it simply turns off. There's no gray area. It's either black or white. So even though this is a simple simple controller, can you think of some disadvantages of using such a controller in different applications? Okay, so it's basically the fact that this is a discrete controller. So I sort of gave the answer already. There is no intermediate or gray state. You either have like a full on or a full off. So this would not work in many instances. So suppose you're controlling a fan, right? You wouldn't always want the fan to go at a full speed or not move at all. You would want some sort of gradation to exist. And that is where you have your continuous control examples, and that's where your PID comes in. Your PID is a very, very powerful type of controller. It is basically used in multiple industries. It's used in power plants. It's used in your cruise controls of automobiles. It's even used in like your autopilot of some planes. So yeah, it's a very powerful control algorithm. I don't want to get into too much of the mathematics behind it because it might be a little much for the high school guys out here. But what you need to know is it consists of three components: a proportional component, an integral component, and a derivative component. Now, it is the combination of all these three components that give the PID like a sort of balanced solution. What I mean by a balanced solution is it is a controller that does its job correctly in the minimal or most optimal way. So, for example, suppose you're trying to have a controller in a self-driving car and you're trying to switch lanes, all right? one of the things that you should do is that a good controller should do is it should go to the desired lane as quickly as possible. All right. So that is called the rise time and settling time. But at the same time, it should go as quickly as possible, but it should also not slip over to the other lane, like a third lane. You'd want to go to the desired lane and stay there as well as possible. So a PID sort of offers that sort of balance. And these are some, so a PID has basically 3 parameters. And by manipulating those parameters, you can sort of achieve like a balanced goal. So some more examples would be like your Segway robot. All right, I'll get to this in the next slide. So this is what I sort of want the undergrads to do as a part of like maybe like their final project or something. So if you've seen the show Arrested Development, I actually wanted to put that GIF. I wasn't sure of the copyright stuff and all that. So you can, there was a character there, his name was Job, and he had like his small Segway scooter, right? It was always funny to me. But yeah, so this is a Segway type of robot. It's essentially an inverted pendulum. So maybe you can try out writing your own PID controller to, balance this robot out. So I'll try to have a bit more mathematics of this in the next week if you guys are okay. Maybe just 1 or 2 slides. I don't want to bore everyone, but yeah, I'll try to include that. So this is a small simulator for those not wanting to get into the mathematics of this. So these are, yeah, sure, I'll do that. So this is a small simulator that I found online, and these are your PID gains. These are your parameters that you can control. These 3 right here. So you can sort of play around with this and just get a feel as to how difficult this problem is. This is not an easy problem, bear in mind. But yeah, so this is something that you would not want to happen. You would not want your pendulum to fall down and start hitting the road and all that. So a huge part of control theory, right? It's all about, tweaking the numbers, because what you initially get will not be the perfect solution. So there are some mathematics to getting a perfect solution as far as these parameters are concerned, but most of the time what you'll have to do is you have to do a lot of trial and error. And that is like a repeating theme in robotics, machine learning, etc. Sometimes there is no science behind choosing the right values. You just have to play around with it. Yeah, so if you guys are successful, I would even, maybe in the final lesson, I can even throw in some, prerequisite material for learning, reinforcement learning. I would not really recommend that, because this is something that is usually taught at the master's level, but let me see if I can give like a very simplified machine learning example for you guys.